Alright, since we now know that carbonyls can be reduced to alcohols using lithium ammonium hydride or sodium borohydride, we should talk about oxidation of carbonyl containing compounds. Remember what we said, reduction is gain. This molecule right here is gaining 2 hydrogens. You see right here there's no hydrogen. Here there's a hydrogen that's added and added. So lithium ammonium hydrides and sodium borohydride, these guys will add the hydrides across the carbonyl. Okay, so the hydride will go here, and then the next hydrogen from coming here comes from the second step, which is the acid. So anyway, it doesn't matter. We are adding hydrogen across the pi bond. We are reducing. Reduction is gain. We are gaining hydrogens. Now, what of oxidation? What of oxidation? Can we add oxygens on the carbonyl area? Okay, so oxidation. Let's see. Oxidation usually happens with aldehydes. Okay, why? Because aldehydes are more reactive. Aldehydes are more reactive than ketones. That's reason number one. Reason number two, oxidation is loss. Oil rig. Oil oxidation is lost. So in this case, we are losing hydrogens attached to the carbonyl. Okay. Alternatively, oxidation is increase in oxidation number. I think we talked about that before. And still, oxidation can be taken as addition of oxygen. So you'll see these three definitions happening with aldehydes. Okay. So aldehydes are more easily oxidized than ketones. I've given you the reasons. Okay, it's more reactive than ketones. Also, you can lose this hydrogen here because it's available to be lost. Here, this is an R group. Ketones don't have that hydrogen on the carbonyl. You have 2 carbons across the carbonyl, so it's not easy to oxidize them. Aldehyde has that hydrogen that gives us an opportunity to oxidize it, even though it's more reactive than ketones for even such a reason. Okay, so common oxidizing reagents include, we talked about Jones when we talked about alcohols, was it in chapter 7? Chromic oxide in presence of an acid, in this case usually sulfuric acid, is a source of H+, the proton. Or you can use potassium permanganate. This one is messy, it's very strong. Or you can use silver oxide or paracids. Okay, the problem with potassium permanganate and paracids, they can also react with double bonds, which means let's say you have an aldehyde, okay, and that aldehyde also has a double bond. So if you react KMNO4 and the paracids, let me just say paracid. If you're wondering what that is, it's just an R group with a carbonyl with 2 oxygens to a hydrogen. These guys will add OHs across the double bond to give you diol, and at the same time they will oxidize the aldehyde to the carboxylic acid. So they are non-selective. They don't just react to the carbonyl. Also the double bond will react. So that leaves us with Jones reagent, which is the best. Now, what someone will ask, what about PCC that we talked about before in the chapter of alcohols? PCC is mild. PCC never oxidizes aldehydes. If it never oxidizes aldehydes, you don't expect it to oxidize ketones. it will also not gonna oxidize ketones. So we are not talking about PCC here because it's mild. You need a strong oxidizing agent. Best choice, chromic oxide, because that can be used to oxidize aldehydes all the way to its carboxylic acid. When this OH, this hydrogen is taken out and oxygen is added, you get O minus. Okay, but because you have an acid with Jones reagent, you end up with acidification of the carboxylate to the carboxylic acid. Okay, so that's why we need the acid in this oxidation. It's oxidation again because you gained an oxygen. Oxygen is not here right now. You end up with it. Oxidation is addition of oxygen. Oxidation is loss of hydrogen. This hydrogen was taken away. This one was taken away. Before inserting oxygen, the hydrogen you're looking right now here comes from what we call workup. When you're acidifying to extract your product, you use an acid. Alright, so let's be specific. So again, the aldehyde has a hydrogen. That hydrogen is gonna go. You're gonna put an oxygen on there, and then the acid will bring it back. You get carboxylic acid. So in general, if you have an aldehyde and you have the Jones reagent, chromic oxide, you're gonna end up with carboxylic acid. So the carbonyl compound is changed to a carboxylic acid. That's the difference. Okay, that's the difference. Similarly, if you use silver oxide, it's not as bad as potassium permanganate and paracids. Silver oxide will allow you to only oxidize the aldehyde, leaving the double bond untouched, which means this one is selective. Okay, chromic oxide is also selective for the carbonyl. Won't touch. If you had a double bond here, the double bond would survive. Won't touch it. Silver oxide is also selective. Okay, do not oxidize those. So only the aldehyde will be oxidized, and as you can see, oxygen has been added. Again, you started with an aldehyde, you went all the way using silver oxide, you went and got a carboxylic acid. Okay, where's the red pen? So you end up with a carboxylic acid. That's oxidation because oxygen has been gained. It wasn't here, now it's there. There's a test for, this test is for aldehydes only. It's called Tollens test, discovered by the scientist called Tollen, and it tests for the presence of aldehydes in an unknown. You know, liquids can be colorless. You see, water is colorless. This aldehyde is also colorless. Methanol is colorless. Ethanol is colorless. Cyclohexane is colorless. Okay, so how can you tell them apart with a test? You just take silver diammonium in presence of a base. It's gonna make a complex, a silver complex, which reacts with the aldehyde carbonyl by oxidizing it. You see, that's an aldehyde, right? So this reagent oxidizes the aldehyde to the carboxyl group or carboxylic acid. That's oxidation. So aldehydes can be oxidized to carboxylic acid. At the same time, we take advantage of that to determine whether we have an aldehyde in an unknown liquid in the test tube. So those taking the lab, 263 lab, this is one of the tests you'll be taught. So as this reagent reacts with the aldehyde carbonyl, it loses the silver. And all of us know the color of silver, right? Color of silver is gonna be shiny. It has a shiny luster. So there's also gonna be smell of ammonia, pungent smell. Smells like fermenting urine. if that's the best description. So this is the diagnostic test. You'll see shiny deposits on the inside of the glass. So there will be shiny deposits on the wall. Those shiny deposits are actually silver. Only aldehydes will release the silver. Ketones will not do it. Carboxylic acid will not do it. Amides will not do it. Esters will not do it. I'm mentioning the carbonyl containing compounds. Okay, so amides will not do it. Ketone will not do it. This is an ester, it will not do it. That's an amide, it will not do it. Carboxylic acid will not do it. Only aldehydes will give you the silver deposit. So this tolerance test is a diagnostic test for the presence of aldehydes. If you are known is as colorless as water, alcohol, acetone, you can use a test. We call it qualitative analysis. You can use qualitative analysis to determine whether you do have an aldehyde. It's not going to tell you which aldehyde is in the test tube, but it's going to tell you the functional group presence an aldehyde. You'll have to use instruments like NMR, IR to determine which aldehyde you have, and mass spec. These are $1 million instruments that we use to determine the structure of organic compounds. So these structures are not make-believe. We can actually determine them using instruments. So yeah, oxidation of carbonyls, especially for aldehydes, can be used to determine whether you have an aldehyde in an unknown colorless liquid. Okay. So what about ketones? Ketones can be oxidized, but to oxidize ketones, you have to use very harsh conditions. You have to use very, very strong, very, very times many, very, 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 very many, very, 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 very strong, okay, oxidizing agent. So that's why I'm saying you have to use harsh conditions, very, very, so very, 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 very strong oxidizing agent. So like nitric acid accompanied by vanadium pentoxide, which is just a catalyst, can help you to oxidize ketones, but doing so, it's gonna chop up the ketone. There's gonna be a loss. So you'll either carry it from this side and replace this group with an OH for that molecule, so you'll end up with this piece. The carbonyl survives, where the group I've circled is gonna be replaced by an OH. Alternatively, you cut this side. Alright, so let me use a different color. So this side will be chopped off. That side will be replaced by an OH. So you're gonna end up with an OH on this side, and of course the rest of the chain will stay. So you notice that this product is just that product, and this is this product with 4 carbons. 1, 2, 3, 4. 1, 2, 3, 4. It depends on which side you slice. Whichever side you slice, you get an OH on that side, whether this side or this side. Okay, and it's because nitric acid is very, very strong oxidizing agents, very harsh conditions, goes to an extent of just cutting the thing apart. Okay, now I mentioned about tautomerism in an earlier chapter. I think that was in alcohols when we talked about phenols. So let me describe it here. These are structural isomers. They are not resonance structures. They are structural isomers. You're moving bonds and elements on the structure. So for example, if I have to draw this structure showing immediate hydrogens, these 2 hydrogens here and here, Those hydrogens are called alpha hydrogens because they are bonded on an alpha carbon. The alpha carbon is bonded to a carbonyl. Okay, let me give you an example here. If I ask you how many alpha carbons we have 2 alpha carbons. How many alpha hydrogens do we have? Can you tell me how many alpha hydrogens we have? We have 4 alpha hydrogens. There is one there, and there are 3 hydrogens on there. So you have 4 alpha hydrogens. Here, I also have 4 alpha hydrogens. They are sitting on neighboring carbons to the carbonyl. That's the carbonyl. So we call those carbons alpha. So it's important you know this because we are about to use those alpha hydrogens in reactions called aldol condensation. So I've shown the black two sets of alpha hydrogens. Okay, those alpha hydrogens can be taken away or rearranged. So if I want to do tautomerism, I would use the lone pair on this oxygen. Okay, so let me take a different color. I'll use the lone pair to grab the hydrogen, and then use this bond to make a double bond, and then give the lone pair that I used here, I give it back. So that's how you get this structure right there. Because this side remains unaffected, the CH2CH3 remains unaffected, but this side you're gonna make a double bond right there. You see now you are left with one hydrogen. The hydrogen is right here, and then here you have a CH3. That CH3 is right there. This hydrogen was grabbed by the oxygen. It's this hydrogen right here. The pi bond opened up, you're left with only a sigma bond, and then you made a double bond right here, which is this double bond. You've not lost any element, you just rearrange the position of the pi bond and the hydrogen, so it's not a resonance, it's structural isomer. Okay, so this structure with the carbonyl is called the keto form. The structure with the OH, which is an O, and the double bond, which is an ene, is called an enol. So the ene refers to the double bond, the O refers to the alcohol. So that's the enol form because there's an alcohol and an alkene. Enol because there's alcohol in all. Yes, keto form because of the carbonyl. So we are converting keto form to enol form, so we call this tautomerism keto-enol tautomerism. Some molecules exist in the keto form more than the enol form, okay, as they have no alpha hydrogen. You see, like this molecule has no alpha hydrogen. To have an alpha hydrogen, you must have an alpha carbon which will bear the alpha hydrogen. We don't have alpha carbon here. No alpha hydrogen, no alpha carbon. This one has an alpha carbon, alright? That's alpha carbon. But see, that carbon has 4 bonds already. So there's no implied hydrogen, so there's no alpha hydrogen. So of course this side there's no alpha carbon. So this molecule has no alpha hydrogens. This one has 2 alpha carbons, but those 2 alpha carbons, they don't have alpha hydrogens because the carbons already have 4 bonds. Remember what we say, carbon must have 4 bonds around it. It could be 4 single bonds, it could be a double bond and 2 single bonds, it could be 2 double bonds. Okay, so here you have a double bond and 2 single bonds, double bond, 2 single bonds. So you're looking at this situation right here. So you don't expect to add hydrogens there. That will make the carbon to have 5 bonds. So no alpha hydrogen. So these structures right here are forever in keto form. Okay? Never tautomerize. To tautomerize, you have to have alpha hydrogens. Okay, now before we talk about this, let's give some examples of keto-enol tautomerism. So if I ask you to draw the enol form of blah 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 blah. So let's say number 1, what is the enol form of this structure? Okay, so the first thing you want to do is to draw your hydrogen. So I have CH3 here, so I'm just gonna say it's a CH2 and a H. That's a CH3. This guy is a CH3. So like I said, the mechanism involves you taking out the hydrogen. Okay, take out the hydrogen, the alpha hydrogen, so to speak, one of the alpha hydrogens. You know, this is an alpha carbon, so it's possible to do tautomerism because there's alpha hydrogens on it. Take out that hydrogen using the lone pair. Move your bond in there, and then this goes up there. Okay, so what happens? You're gonna end up with OH on top. Okay, and then you're gonna end up with a double bond and CH2, because this arrow makes a double bond. Pi bond opened up, you're left with a sigma bond. The oxygen gain a hydrogen. So this will be the enol form, because you have the ol part and the in part, the alcohol part and alkene part. This is a keto form. Okay, let's do the next example. So now, what if you're given this structure? This time you have at least I'm saying it's a CH3, so I'm just showing one alpha hydrogen. You have at least one alpha hydrogen there on that alpha carbon. You have another alpha carbon here. Okay, so there are two hydrogens. I'm just showing one, and you have another alpha hydrogen here. Okay, there are three alpha carbons with three sets of alpha hydrogens. We are gonna use one of the hydrogens out of the three sets for tautomerism. So let's say you want to make a tautomer out of this hydrogen. The same process occurs. Grab that hydrogen, use the bond to make a double bond, and this gives back to oxygen because it used its lone pair. So in that case, you will end up with this structure. So oxygen grab the hydrogen. Now you're left with two hydrogens here, so CH2, and then of course the rest of the structure. The same can happen on the other side, where this oxygen can grab the hydrogen. Let me show it in red. So let's say we have this alpha hydrogen here. So take out the hydrogen, make a double bond, give back the lone pair that was used to take the hydrogen. So this will be an alternate enol. That's an enol. This is the keto form. It's actually a diketone. That's two carbonyls of the ketone, but it's also the keto form because of the presence of carbonyls. So now we have one more option where we can take out the hydrogen from in between the carbonyls. So let me just show the two of them for purposes of teaching. So use the lone pair, take this out. You can also use this as a lone pair. Whatever you get is just the same. It's just like these two guys are the same. So showing one is enough. So I'm just going to show the one having a double bond on the left instead of the right. It's just the same thing. So take that hydrogen, make a pi bond. This goes. So you end up with OH. Okay. And then there's a double bond. And then there's a carbonyl. And then there's that. So you either gonna make that or you make the other option where the double bond, the in part will be on the right. They are the same. These are the same. They just flipped over like a pancake. So this will be the enol form, and this is the keto form. Actually, it has been proved that when you have diketones, they would most likely want to stay as enols, not keto forms. Where you have one carbonyl, it will want to stay in the keto form, but where you have two carbonyls sharing an alpha carbon, the inner form will be mostly favored, so the equilibrium will lie to the right than the left. Okay, so let me show that. In this case, the inner form is more favored than the inner form, but in this case, the keto form is more favored than the inner form. Okay, because there's only one carbonyl. Here you have two carbonyls sharing an alpha carbon. Inner form is more favored. Because going further to explain in deeper organic chemistry is because the lone pair here will form hydrogen bond with this hydrogen, get a 6-membered ring, which is more stable. So inner forms are most favored whenever you have diketones than the keto form. Where you have one carbonyl, the keto form will be more favored than the inner form. So the equilibrium lies to the left here the equilibrium lies to the right. Alright, so I have talked about alpha carbons, which in turn gives us alpha hydrogens. Why is it that we can take out alpha hydrogens? The reason is because the alpha hydrogens are acidic. So let's talk about acidity of alpha hydrogens. The alpha hydrogens are way more acidic than the normal alkane hydrogens. We can evidence that by pKa. The evidence is using pKa. Remember what we said? The higher the pKa, the lower the acidity, and vice versa. The lower the pKa value, the higher the acidity. Remember, the pKa is just a numerical representation of the ability to lose the proton from a structure. So here you're gonna need a lot of energy, so to speak, to take out a hydrogen from the CH3 to get a CH2. Okay, so alkanes are extremely weak acids. Okay, but now what about ketone or an aldehyde having an alpha hydrogen? So these are alpha hydrogens. I can show one like that. So like this guy can be taken out by a base. So let's say we use a base. The alpha hydrogen can be taken out using a base, and then the two electrons, the bond, are donated to the carbon. So you end up with a negative charge. Okay, so you form a carbanion because it's a carbon bearing a negative charge. Carbon bearing a negative charge. Negative charges are called carbanions. These carbanions can be used as nucleophiles, because remember what we've been doing with nucleophiles. So long as you have a lone pair, and even more when you have a negative charge, that species plays the role of either base or a nucleophile. So whenever the B takes out the hydrogen, what you're gonna get is EH. Alternatively, you can write it as B negative H plus, and that's why this H plus was included. Look at the pKa. The pKa of taking out this hydrogen is 19, which means if you get a stronger base, it's possible to take that out, because strong bases could probably be having a pKa about 40 or so, which can take out that hydrogen. But a pKa of a base of about 40 will not, a pKa of about 40 of a base will not be able to take out the hydrogen from this carbon, because that number is lower than 50. So if this is 40, or if that is 28, 27, that can take out that hydrogen. Okay, comparatively you can take it out because it's a stronger base than this hydrogen, so to speak. Alright, so there's gonna be an increase in acidity. Carbonyls are electron withdrawing groups. Trying to explain why alpha hydrogens are acidic. Trying to explain why alpha hydrogens are acidic, we can use dipole moments. Okay, dipole moments. Let me write that clearly. My pen slid on the surface. I want you to see this very clearly. So you can use dipole moments to explain why alpha hydrogens are acidic. So carbon is less electronegative than oxygen. Dipole moments point towards oxygen. So you can imagine the electron density being pulled out towards the oxygen. This hydrogen will be less electron dense. That's why we give it a partial positive charge. And that's why it's possible to use a base to take out this partial positive charge, because opposite charges attract. So the base will deprotonate the alpha hydrogen. You use these two electrons to donate them to the carbon, and that's how you make your carbanion. The special name for the carbanion is called an enolate, because after tautomerism you're gonna get what seems to be like an eno, but there's a negative charge, so it's enolate. So once you make your carbanion, you use your lone pair to make a double bond. So start your arrow from the lone pair to make a double bond. The pi bond opens up. You have two lone pairs here. Now you have three of them. So, you know, if this was OH and we had a double bond, we would have called this an eno. But because the OH is missing and you have a negative charge, we call it an enolate, because now this is a salt. Okay? Remember, whenever we make salts in organic chemistry, we always add the ATE, like carboxylate. You see, like this one is a carboxylic acid group, right? But once you introduce a base and you lose the hydrogen, you're gonna get a carboxylate. So we add the ATE whenever we make salts, carbon containing compound salts. So that's an enolate. Enolates and the carbanions will always play the role of a nucleophile, and we're gonna use that very soon in aldol condensation. So there is resonance stabilization, which makes it possible to take out this hydrogen. So those are the two reasons why the alpha hydrogen are acidic. One reason is dipole moments, which are causing inductive electron withdrawal through bond. The second reason is once you take out the alpha hydrogen, the salt that you make is resonance stabilized. So with that foundational information of making enolates, okay, we are now ready to do reactions. So we just say that you can do resonance stabilization here from the carbanion to the enolate. So we can do what we call aldol condensation. Condensation reactions always result to loss of H2O, and we are taking out alpha hydrogens in aldehydes or ketones and combine those two together. Again, that's condensation, when you bring two molecules together. Okay, so two facts about condensation: you're most likely gonna lose water, and you're fusing and bringing together, clicking two molecules together. So the enolates will act as nucleophile. Remember what I said? You can use the enolate as a nucleophile, or you can use the carbanion. The carbanion is where the carbon has a negative charge on it. Okay? The enolate is where you've done your resonance. Now you have the O minus and the double bond is right there. Okay? So both of them, the carbanion and the enolate, can both be used as nucleophiles to attack another carbonyl containing compound. Okay? For example, the product of beta hydroxyaldehyde or ketone will have an OH and a carbonyl. Now, one would wonder, why do we need OH? You need the OH to make an enolate. OH minus is a strong base. Okay, so that takes out the alpha hydrogen. You get your carbanion. So you get your negative charge here. The aldehyde is on there. And then this carbanion can be used as a nucleophile to attack another aldehyde. of itself. You see how it says 2? So it attacks another aldehyde of itself. Let me just use a different color. I know the mechanism is coming up, but I want to use this slide to at least give you an idea what's happening. So let's say it attacked the black aldehyde. The carbanion attacked the black aldehyde. What do you end up with? Okay, so you're gonna end up with your red molecule joined to, so I'm gonna use a different color. So let's say this bond was blue, attacking this, and then this opens up. So it's gonna join to the second black molecule. Now you see how the carbonyl opened up. So that carbon should have an O negative, which used to be the carbonyl. And then you still have your hydrogen on that carbon, this hydrogen, and then you have this chain to the R group. Okay, so now what do you think happens if you add an acid? If you add an acid, the O minus will grab the acid, so you end up with this combined structure. Okay, so you end up with OH, the hydrogen, and the black R group. Alright, so now let me now show you why this is the same as this. So let me show you why this product is the same as this product. So this part here with the OH is this black part here. Okay, the blue bond here is this blue bond here, the one that we used to click the two molecules together. And of course the red part here is the same as this part right here. So you fused two of these molecules, taking advantage of the carbanion as a nucleophile to attack the second molecule. So this is molecule number 1 attacking molecule number 2 after it was transformed to a carbanion or an enolate if you do resonances, and then followed by acid workup. The O minus is transformed to OH. That's where this H came from. So let's look at the mechanism on the notes. So this came from your KOH. You use the base to take out the alpha hydrogen sitting on an alpha carbon, and then this bond is taken onto that carbon. You end up with the carbanion. Alright, the carbanion can do resonances, which will give you the in part, the diabond, and the all part, which should be, this should have been an OH, but the H is missing, so we say olate, enolate. Both these two guys plays the role of a nucleophile. Okay, so once you made it, you use it to attack a second equivalent. So this is the second equivalent or second molecule, because the first molecule is used to make the enolate. The second molecule is attacked by the enolate. So let's use the carbanion. You can use the enolate or the carbanion to attack. Let's use the carbanion. So the lone pair on the carbanion alpha carbon is used to attack the carbonyl of the second molecule. Why? Because we said when we started this chapter that carbon is partially positive because of dipole moments, right? So the negative charge is attracted to the partial positive carbon. You attack it, but this is a new bond wanting to be made. You already have 4 bonds. If you make this bond and leave it like that, you'll have 5 bonds around the carbonyl carbon. That's why we have to open up the pi bond to keep 4 bonds around the carbon bearing the oxygen. Okay, so this hydrogen is still there. Now you have a negative charge on oxygen. Reason being, you had 2 lone pairs, now you have 3 lone pairs. Do your FC formal charge calculations, you'll find it should have a negative charge. Now, organic molecules don't like to be negatively charged, so we acidify. In this case, our source of acid is water because we are in the presence of a base. So the oxygen will use its lone pair to take out the hydrogen, and that goes away. Yeah, I know you're wondering, water is an acid? Water can play the role of a base or an acid. Because you're in the presence of very strong base, now water becomes an acid. Because the pKa of water is only 15. If this base can pull out a hydrogen that has a pKa of 19, the base can also pull out a hydrogen from water which has a pKa of about 15.5, 15.7. So we use the water as a source of hydrogen. Alternatively, you can add a weak acid in the flask. It should do the same thing. You protonate the O- to the OH. That will be the mechanism. Finishing with protonation, very, very similar to what I explained here. So this reaction is called aldol condensation, not because we are starting with an aldehyde. Okay, so that's not the reason. It just got the name because aldehydes are most likely to do the reaction because they are more reactive than ketones. But it's aldol condensation because you're condensing, you're fusing two molecules together, and you're gonna lose some water. Okay, how do you lose water? The OH taking out the alpha hydrogen gives you HOH, which is water. Okay, so can you do aldol condensation with two of these? The answer is no. Why? Because there's no alpha hydrogen. So this will play the role of the second molecule. In other words, it's going to play the role of an electrophile, and this will play the role of a nucleophile because we can make a nucleophile out of it. If you use a base, the base can take this hydrogen out, you get a carbanion. Okay, from the acetone, you get a carbanion. Once the base takes out that hydrogen, you get carbanion and of course the conjugate acid out of it. So this plays the role of a nucleophile. This will play the role of an electrophile because nucleophiles attack electrophiles. You attack that, this opens up. So let's draw the immediate product here on the mechanism. So nothing happened on the chat bureau side. The oxygen opened up as we attacked the carbonyl. Now you have a negative charge. The hydrogen is still there, and then the piece that attacked it will be here. So I'm gonna use a blue bond again. Probably I should have used, just assume this arrow was in blue. Then this bond here is that arrow in blue. The arrow was used to attach the carbonyl. It was used to attach the carbon of the carbanion, right? So this carbon is attached to the carbon of the carbonyl of the electrophile as it opens up the pi bond to get O-. So now you've fused them together, you've condensed them together, but is that all? No. So you can come and finish up the reaction using an acid. It could be water, right? If this base is OH-, then this BH will be H2O because OH- would simply gain the hydrogen to give you H2O. So let's use H2O as an acid. Use a lone pair out of the enolate. I told you organic molecules don't like being charged. If there's a way to keep neutral, that's what they'll do. So the lone pair of the oxygen accepts the hydrogen. You get your OH, and that's the product. Of course, the byproduct here is OH-, which is just recycled for the second round of aldol reaction. Okay, so previously here we did aldol with two aldehydes, right? Remember I said it doesn't have just to be an aldehyde. This is an aldehyde reacting with the second molecule of an aldehyde. Let me clean that up. So that's an aldehyde reacting with the second molecule of an aldehyde. After making the carbanion out of the first aldehyde, you attack the second aldehyde. But it's also possible for an aldehyde, okay, to react with a ketone. It's also possible even for a ketone to react with a ketone. The key governing factor is you do have to have an alpha hydrogen on one of them. So you can do aldo condensation between two aldehydes, or an aldehyde and a ketone, or a ketone and a ketone. Okay, but to do that, you have to decide which molecule play the role of a nucleophile, which will play the role of an electrophile. Look for alpha hydrogens. If they are missing on one, that's easy because now you know the other molecule which has alpha hydrogen will play the role of a nucleophile after the base takes out the alpha hydrogen to give you the carbanion or the enolate form. If you do resonance, you use that as a nucleophile to attack the second carbonyl containing compound. Click them together, you get an alkoxide structure. Protonate the O-, you get your alcohol. So now that we've been making alcohols products which of course have OH, we usually call these products we call them aldo product, because we have an OL, we have an alcohol. It's an aldo product there. This is also an aldo product. So this OH can be lost. This OH can be lost by taking out a second alpha hydrogen. So if a base takes out this second alpha hydrogen, make a double, this loses. That's another example of condensation. So we will talk about that shortly. Okay, so now the problem is that whenever you have ketones, there's going to be a lot of mixtures, because you can take out this hydrogen and that, or that hydrogen. So if you take out the first hydrogen using a base, guess what? You get an enolate, okay, with the double on this side. But if you take out this hydrogen, you get an enolate on this other side. So enolate, to the left, to the right. So this leads to mixture of aldo products, because now from one molecule you can get so many mixtures, but I don't think I'll go much into that. Let's take our aldo products. Remember what I say an aldo product is. After you did your mechanism, you get your OH on your product. That's aldo. This is an aldo product. So the aldo products can be taken one step further. In presence of an acid, not or heat, I'll say, and heat. It usually helps to take the process further, to make a double bond. Okay, so I'm gonna describe the mechanism here. It's not a must, but I just want you to be aware that you can lose extra water to justify this is aldo condensation. So in presence of an acid, what happens? What happens in presence of an acid? So the first step is the OH of the aldo product will accept the proton from the acid. You know, H3O plus is just a source of H plus. OH are not good leaving groups, so we are trying to make it good leaving group to leave as a weak base, which is water, rather than leaving as OH minus, which is a strong base. Okay, and you have now your alpha hydrogen there, so you can use water. If this is dilute acid, it must be diluted by water. You can use water or a base to take out the alpha hydrogen. This comes in and this leaves by a process of E2. You're taking out a hydrogen, you're making a double bond. As that leaves, the reaction is concerted. That takes you to this point. You see water is leaving, so you get this water by process of elimination. Okay? So you end up with what we call an alpha beta unsaturated ketone. And that will mark the end of this chapter. So I think let me do examples, random examples out of this chapter, just to wrap it up. So I'm gonna test I'm gonna test your understanding out of the chapter. Random questions out of the so many reactions we've talked about, which probably you must have felt it was boring. But hey, this is organic chemistry. It's about reactions and mechanisms. So question 1, what will be the product if I give you this molecule reacting with methanol? Allow me to use a different color. If I give you that molecule reacting with methanol, and I tell you that this is only one equivalent in presence of an acid. So again, you have a carbonyl containing compound, you have an alcohol. If you remember very well, this is how you make hemiacetal. So the shortcut is only the OR group will be added. That's the shortcut. Will be added onto the carbonyl. The carbonyl itself is going to be turned to an OH, and the rest of the structure stays. So the carbonyl is converted to an OH. Only the OR group is added to the carbonyl, which in this case is OCH3, and that's how you get your hemiacetal. Now, what if I give you the same carbonyl compound? It could be any carbonyl compound, a ketone or aldehyde. This time, I'm giving you two equivalents of an alcohol. Okay? Two equivalents of an alcohol. We always want it to be acid catalyzed. So, two equivalents. So, the reaction will go through the hemiacetal, alright? But it will not stop there. So I'm just gonna show you the intermediate step. So the carbonyl will be converted to OH again. That's your hemiacetal. But because you have two equivalents, the final product that I would have been grading is where you'll have OR. So eventually you'll have two OR groups. In this case, the ORs comes from the alcohols, and then the carbonyl backbone stays the same. Okay, so notice that the carbonyl is gone. It's replaced by the two OR groups from the alcohol. That's the shortcut. You end up with an acetal. So whenever you have excess of the alcohol, you end up with an acetal. There was a different, I'm just going to use the same carbonyl. There was a different type of alcohol that we used. This time around, it's one equivalent, but that one equivalent has two OHs on it. So no need to say two equivalents, because the single one equivalent brings the two OHs. So in this case, you're going to go straight ahead. In presence of an acid catalyst, you're going to go straight ahead to make your acetal, but your acetal is going to be a ring. We talked about that and said that this reaction is carbonyl protection. Okay, we use the ring to do protection of ketones and aldehydes. So let's say you are doing Grignard reaction. You'll want to protect the carbonyl before you do Grignard. Okay, if you want to break this out and go back to where you started, all you need is to add HCl and heat, or H plus and heat. It hydrolyzes the protecting group and deprotects it. So I'm just giving you a summary of some of the reactions we've done. Okay, so keeping on with the examples, I think we are on number 4. So if I give you this molecule and I tell you to react it with this molecule, What is the name of that reaction? So we'll quench the reaction with H+. What's the name of this reaction? This reaction is Grignard reaction, addition reaction across the carbon, carbonyl. So I told you, if you're given a Grignard, forget about the metal part. You have 3 carbons. The last carbon, which happens to have 2 hydrogens, will be taken to be a nucleophile. You use that to attack the carbonyl and this opens up. Okay, so I'm just giving you a draft of the mechanism. So you end up with O minus, because now you have 3 lone pairs, and of course let me use green for this arrow. So that's the bond that was made by that arrow, and then you have 3 carbons, 1, 2, so you have 1, 2, 3 carbons. So this is the CH2 that did the attack. Now the hydrogen in blue is still there. This hydrogen on the aldehyde is still there. Okay, you see how it says then H+? So this oxygen will take that hydrogen to make OH. So Grignard reactions always converts the carbonyl to an alcohol. Always convert the carbonyl to an alcohol. So the trick here is to make sure that you have the same number of carbons total. So here you have 4 carbons, here you have 1, 2, 3. You have 3 carbons, so 4 plus 3 equals to 7 carbons. So let's see, do I have 7 carbons? 1, 2, 3, 4, 5, 6, 7. Correct. And where the carbonyl was, now it's an OH. So I got a secondary alcohol out of an aldehyde. If it was a ketone, I'll get a tertiary alcohol. So let's do an example for the ketone with Grignard. So let's say this is my ketone. Okay. And this time my Grignard looks like this. So this time my Grignard looks like this. MgBr. Again, I told you, it could be MgBr, MgCl, MgI. I told you the best way to look at it is to take it as this carbon bonded to the metal being negatively charged. Okay? Because you're going to use it as a nucleophile, the carbonyl will play the role of an electrophile. So I'm going to use red to attack the carbonyl from the back. It takes what seems to be SN2 back attack. So what do you get? Okay, what do you get? So keeping my number of carbons constant, I know my oxygen here now is going to be negatively charged because now it has 3 lone pairs of electrons. My metal is still there. The red arrow that did the attack is the new bond, newly formed bond. Okay, and then I join my purple 4 carbons onto this one. 2, 3, 4. 1, 2, 3, 4. Now, if it says then H3O plus or H plus, then you would expect that that oxygen will be protonated. Okay, the oxygen will be protonated, which means it's gonna gain a hydrogen. Make sure that the number of carbons sum up. Okay, so I'm just using color code so you can track what I'm doing. So I have 1, 2, 3, 4, 5, 6, 7, 8 on the longest chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's see, am I missing a carbon? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. I'm missing a carbon somewhere. Let's find it. Oh, it's the methyl. It's this CH3 right here. So let's see overall. 1, 2, 3, 4, 5, 6. This has 6 carbons. This has 4 carbons, so it's 10 carbons total, including the substituent. So this should have 10 carbons total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I'm okay. Alright, so in summary, if you start with this carbonyl containing compound and you have a 4 carbon Grignard, you should expect to have an OH here. If the last step was acidification, you get OH, not O minus. And of course, the rest of the Grignard carbon structure that was added. So that's your Grignard. Another reaction we talked about is addition of acetylene. So if you're given acetone, this carbon, and you're told that it should be reacting with a triple bond that's negatively charged, the triple bond could have any R group. So, you know, alkynes are acidic. So if you add a base to a terminal alkyne, this hydrogen will be taken out. And that's how you make the nucleophile, okay? This nucleophile, and you can use that nucleophile. You can use that nucleophile to attack this carbonyl. I was hoping to use a different color. So let's assume this arrow is green. Attack the carbonyl and this opens up. So mechanistically, you're going to click the top part with the green arrow. So let's see which color is that. Men are colorblind. So you'll get the two methyl groups, which is this, and the O minus. Okay, and then you have the red structure, which is just the triple bond. Remember, triple bonds have linear molecular geometry, right? So if it goes forth on the arrow giving you an acid, the acid can be used to protonate. The O minus organic molecules don't like to be charged, okay? And your product will look like this. So let's see. I need a red, so this will be your product. So in summary, if you are given a carbonyl compound and you're given a triple bond that's negatively charged, you click them together. If it says that it's gonna follow up with H plus, the O minus will be converted to OH. So again, you have to maintain the number of carbons that you're joining together. Okay, so this is just what I drew. It's just what I do here. So this is where you join the two pieces together. The OH comes from the carbonyl. This reaction is sort of an SN2. You are adding alkyne on carbonyl. Okay. That's not the only one we talked about. We also talked about addition of HCN, which is cyanohydrin formation. Okay. Cyanohydrin formation. So if you have a carbonyl containing compound ketone or aldehyde and you're adding HCN, the summary is that you will be adding your H on the oxygen. This is just a shortcut, and the R groups will stay. The hydrogen part of HCN goes to the carbon of the carbonyl. The CN part of HCN goes to the carbon of the carbonyl. So you see, you would have added H and CN across the double bond. This structure here is called a cyanohydrin. Hydrin because there's an OH sharing a carbon with the CN. Cyano because you added the CN. Okay. That's not the only reaction. We also did addition of water. Okay. Which gives you geminal alcohol. You know, water is just H and OH. So let me use a different color code here for water. Okay. So we are trying to make what we call a gem alcohol. That is called geminal alcohol because the alcohols are on the same carbon. Okay. So typically, again, like we did a shortcut here, the H is gonna go on that oxygen, the OH will go on that carbon. So I'm just going to give you that shortcut to quickly identify the product. Okay. That's it. H goes to the O, OH goes to the carbon. You get a geminal alcohol. Aldo condensation. So for aldo condensation, we said if you start with two carbonyls, one has to determine which carbonyl has. So for example, let me use this one where there's no alpha, but here there's an alpha hydrogen. So one would use that if we have two equivalents of this. So let's say we have that's reacting with, and this part you really have to practice. Aldo condensation is not very obvious. You have to practice. Let's say we are combining these two guys. So let's take this one reacting with a base to make a carbanion. So you're gonna end up with a carbanion. So we are trying to react the first one in order to create a nucleophile and use the nucleophile to attack the red one, which will play the role of an electrophile. So you'll have a negative charge on that CH2. So this is a CH2 now. You started with a CH3. Now it's a CH2. It's gonna be a negative charge because of the lone pair. And then you use that as a nucleophile. You'll use this as a nucleophile to attack. Different color, please. Use this as a nucleophile to attack the carbonyl of the second molecule. So what you're really doing is creating a bond between the two. You're creating a bond between the two. So let's say this is purple CH2 and this is the purple carbonyl part of the molecule, like this structure right here. The black is this arrow and it's clicking onto the red carbonyl. So that's the red carbonyl, which will end up giving you O-. This CH3 right here is this CH3 right here, and of course we have to show the ring that's on the same carbonyl carbon. So if you do acid workup, the O- will definitely be OH. CH3 is still there, the ring is still there, the red ring is still there, and the purple ring is still there. So I'm just gonna draw the purple ring here. So in summary, you get an OH, okay, and the carbonyl, and I told you this is called aldo product. Now, if you take the aldo product towards one more step, heating in presence of an acid, this OH will go after base takes out this hydrogen, you make a double bond. The OH will leave as water, because this H plus will be put onto this oxygen, so this leaves as water. So in that case, you'll get a double bond. So it depends on what you're asked in the test or the quiz. Either you're drawing the aldo product or the condensed alpha beta product. Okay, because this will be a final product after water leaves. This only happens if there's a step of heating. And this will be the last review on it. Carbonyls can also be reduced. So there are two reducing agents. You either have lithium aluminum hydride or sodium borohydride. The key part is that these guys are just giving you hydride. So if you start with a ketone, the ketone will be reduced to secondary alcohol. If you start with an aldehyde containing an R group, that will be reduced to primary alcohol, because you're into the hydride. So if you're using lithium aluminum hydride, all you're doing is adding a hydride. See here, there's no hydrogen. Now you do have the hydrogen. So that came from the reagent. Same thing, if you use sodium borohydride or lithium aluminum hydride, here you're adding the hydride. You had one hydrogen, now you have two of them. Anyway, this is a primary alcohol. Okay. For oxidation, aldehydes are the best ones to be oxidized, and if you use chromic acid, they're gonna be oxidized to carboxylic acid. Okay. If you use PCC, there's no reaction because this is mild. Okay. If you use silver oxide, it's still gonna oxidize the aldehyde to the carboxylic acid. Okay. I think that's a good overview and good way to end the chapter or end the reactions of carbonyls.